Hello, my name is Ken Buesseler. It's my pleasure to be here. I'm a scientist, a marine radiochemist, to talk about the impact of Fukushima Daiichi and the release of radioactivity to the ocean. So I've got some slides I want to show you. And here's the first one. And basically, the topic today, as I said, is about the release of radioactivity from Fukushima Daiichi that started in 2011, 10 years ago. So my name is Ken Buesseler. As I said, I'm a senior scientist at this institution called Buesseler Oceanographic Institution. We're physically about 2 hours from Boston on the East Coast of the United States, and we have about 1,000 employees studying all aspects of ocean science, from biology to chemistry to geology and the physical properties. We also have a very strong engineering team and several research ships that fly the ocean to do research. My work is related, as I've told you, to radioactivity. And here's a picture of me just to show you that in 2018. Behind me is Fukushima Daiichi nuclear power plants. We've been going to Japan as early as 2 months after the initial releases in March of 2011, about once a year, recently and more recently in collaboration with Japanese. It's a Japanese research vessel I'm on about 1 kilometer from the release point in 2018. Today, I'm going to talk about several things. Basically, I want to give you a 10-year perspective on what the levels of radioactivity are. I'll focus, because of time, on seawater and marine life. I'm also going to get into a few surprises. As scientists, there are things we learned that we didn't really know about radioactivity in the ocean, and that relates to a source in some of the beaches. I'm also going to talk to you about what the future holds, and one of those stories is about the potential release of radioactivity that's being considered related to thousands of tanks that are on site that contain liquid radioactive waste. And then I'm going to announce an event on March 4th that we're hosting on a similar topic. So we're going to start with radioactivity in seawater. Typically, this is a Japanese research vessel. We might raise and lower tubes into the ocean to collect that water, bring it back on board, and take that to the lab for our measurements. So here's an example of measurements of cesium-137. This is a radioactive form of cesium, has a 30-year half-life, so it stays around for decades. And each dot is a seawater sample. And each sample was collected at one point closest here to Fukushima Daiichi in the ocean. So these are as high as the levels got. And we're showing here a time frame from March 2011, almost a year later. So this is the first year, basically, and what the levels of cesium were as it was collected near the docks of Fukushima Daiichi. Now, the units I'll be using are becquerels per cubic meter. A becquerel is a decay event per second, and a cubic meter is a pretty big volume of water. This is, in fact, a pretty small amount of radioactivity in a big amount of water. So these numbers get pretty high. What's astounding to scientists as we look at these numbers ranging from 1 to 100 million, so that the levels prior to this accident weren't zero. We've had radioactivity in the ocean ever since the nuclear era began. In particular, the fallout from atmospheric nuclear weapon testing leaves a background, a residual level of cesium, about 2 becquerels per cubic meter in these units. The highest levels we've ever measured after Chernobyl were kind of in the 10 to 1,000 range. So immediately, the eyes taken by these numbers, 10 million, 50 million, that happened early on, peaking in early April of 2011. So based upon this data alone, and this isn't my work, this is from TEPCO, the organization that operated the nuclear power plant, and the Japanese monitoring, this is truly an unprecedented release of radionuclides. These are higher than we had ever seen after an accident such as this. Now, let's look a little bit further out. We said we're going to look over 10 years. Well, this now is a time scale from 2011 here on the left to 2020 on the right. The same location, so these are the highest levels you would find in the ocean, the same isotope and the same units, showing those early data. Now, kind of the good news is the levels dropped quickly. They were able to contain the releases. A lot of this release was related to cooling water being applied. If you remember the images, they used helicopters, they used firefighters to kind of cool down and get that reactor under control after it had overheated and released the radioactivity after several explosions. So that's good news. It starts to level off though. It doesn't go back to this number of 2. And so here out to 2015, where it levels to about 1,000 becquerels. And then as we go out in time now to 2020, and even today, if you were to measure, you get numbers maybe about 100 becquerel per cubic meter. So we know there's still a source, otherwise we'd be back down here at 2. So that's the first conclusion of looking at just Japanese data that have been released on a regular release, not just from this location, but several locations. But I think what people want to know, and they ask me, well, what does it mean for me? What does it mean for human health? Well, one way to measure that is by drinking water limits. Now, no one drinks directly ocean water. Some countries do desalinate water and drink it. But basically, levels got down to here about 10,000 of these units, becquerels per cubic meter, which is the Japanese drinking water limit, relatively quickly. But I think more importantly is to put these in perspective of harm to marine life and harm to human consumers of seafood. So as I introduced my role at Woods Hole Oceanographic Institution, we're a non-for-profit. I don't work for the government. I don't work for IEA, but I have looked at the literature of where are the levels that would cause direct harm to marine biota, fish, shellfish and things. And more or less, and these should be fuzzy boundaries, but somewhere around 1 million becquerels and above. So during that first month and a half is when you might have direct reproductive effects on marine biota, death, mortalities. Well, we rapidly got below that after the first month. So that's relatively good news, but I call that the red zone. And by that same token, I think there's a very large range down here to about 1,000 of these units when we have to be concerned about consumption of seafood as humans. So if you internalize a radionuclide like cesium, it can have effects on human health. And I'll show the data in fish shortly after this. But when you get below about 1,000, the fish have levels that are below that concern level. So I put a lower boundary, and again, it should be a fuzzy boundary here, about 1,000. And you'll see that somewhere around 2015, 2016, we get into the green zone, because we can also use studies in health physics to say, well, when would we not see appreciable effects on humans? And that's when you get below about 1,000. And so that's where I think we are kind of good news, bad news here is we were at levels that would cause direct harm. We had several years when we need to be concerned about consuming seafood. They shut down fisheries because of that. And we're now in this green zone, but we're not completely out of the woods yet. I still think there's definitely attention that needs to be paid to those levels, and ongoing monitoring is warranted, even 10 years later. So where does it go? I'll talk about that before I get to the seafood. Well, I just love this image. It's just so beautiful. This is a NASA rendition, a model of ocean currents. You can see Japan here in the Pacific, and these white lines are the strength of the ocean currents. The Kuroshio is the strongest one here that moves water across and away from Japan. Fukushima Daiichi is kind of where, if you can see my pointer, just north of that current. So when radioactivity gets in the ocean, it will move with those currents. It will stay encapsulated by some of these eddies, these circular motions that will hold it for longer periods of time. But essentially what would happen, anything that goes in the ocean, it's going to be driven by physical currents away from Japan. Now, let's put that in terms of cesium, the isotope we've been talking about, and how quickly that would move. So this is a model prediction by Rossi and coworkers, high numbers near the coast of Japan in 2011. And let's see what happens if we predict where it's going to go. Well, by 2012, it's already crossed over half of the Pacific Ocean. Here are the islands of Hawaii, and here's the US, West Coast, Mexico, Canada, and Alaska up here. So it moves rather quickly. Those oceans transport water very rapidly across the Pacific. The colors get lighter because as you move, you have dilution. Isotopes, not all of them, but cesium in particular and several others become diluted. They become less, the levels decrease with dilution and mixing of this dark blue water with the source here off Japan. So I'm just going to let this run out. We'll do it again. 2012, 2013, and 14, we got concerned on the west coast of the US what the levels might be. I don't have time to talk about that, but we actually did some measurements involving citizen scientists help us collect. And indeed, we found numbers here that were a few, 3 up to 10 becquerels per cubic meter on the west coast of North America. And so we've been able to improve these models by making measurements over here, but also realize that by the time that radioactive plume hits the west coast, we don't expect to see those same health effects. This would be definitely in that green zone that I showed you earlier for the waters closest to Fukushima Daiichi. And in fact, these levels here, say 10 off of the west coast, are the same or even lower than they were in the 1960s when we were actively detonating atmospheric nuclear weapons. So we've seen levels like this before off the US west coast. So let's move on. Let's talk about what most people care about, which is seafood, things that they might be exposed to by their choice in eating sushi or whatever at your favorite Japanese restaurant. What we've done here is we've plotted now becquerels, that same unit of radioactivity per kilogram of fish. And we're going to look at a series of data. These come from Japanese Fisheries Agency. Each dot, like before, each dot was a sample of water. Each dot is a fish sample. And we've got this scale going from 10 up to 1,000 becquerel per kilogram. And I'm only showing you data from the bottom dwelling fish. These happen to be the highest. And from this red area, which is the prefecture of Fukushima Daiichi. So again, the highest levels. Now, two things popped out to me when I pulled this data together. This data were being openly released, but not put in a graphical form like this, where I show the data from April of 2011 through December of 2012. But any one point, there's a wide range. So you can't really say they're not all the same. And that depends on their diet, how much time they spend in the area that's impacted. But the other thing to note is that a majority, or about half of these fish, are above this line, and that's the line at 100 becquerel per kilogram, the limit allowed in Japanese seafood. Now, this is quite a conservative threshold. In other words, other countries, like in Europe, that number is 500. Where I live in the United States, it's over 1,000. So they set a very strict limit above which they would close these fisheries down, and they did, so these would not reach the marketplace. These were studies that were being done, carried out primarily by fishermen who would collect their catch and bring it in for analysis. But it was surprising at first that this level was not going down very quickly. So for at least the first couple of years, they had concerns with many of the fish being above their limit, had a big impact on Japanese fisheries. Now, they didn't just measure a few fish. This is over 50,000 data points from 2011 to 2016. And I've used two colors. Again, the brown is those bottom dwelling fish. They tend to be a little bit higher than the light blue color here, which is the pelagic ones that swim up above. And that's because of the feeding on organisms and materials on the seafloor that have additional radioactivity. So there's a general difference between them, but you'll see most all of the points here by 2015 start getting below the line. So I guess the point of this isn't so you look at each point and say, wow, what can we learn? But it's hard to manage a situation when the levels of individual fish can be many thousands or down here near the detection limit of their particular setup. But they certainly reached levels that were lower than the Japanese limits within a few years, not 2 years, but 4 or 5 years. So let's look at that a little bit more from the perspective of the Japan Fisheries Agency. They had to make decisions about when to open and close fisheries. So we have here the number of samples in different quarters of the different years, 2011 up to 2016. They were analyzing about 10,000 fish per year as part of this study. These happen to be fish from greater than 20 kilometers off of Fukushima Daiichi. So this is where they expected there to be high levels. And the orange is an indication of how many of those fish were above their limit. In that first year, about 50-50% of the fish were above their limit. And as you'll see, this kind of rapidly disappears. And the take home from all this monitoring, if you look at the percent of the fish that are above the limit, they start out above 50%, but they reach a point 2014 when they have not found a single fish that are above that limit. So that's when you started to see selectively opening of certain types of fisheries, the pelagic fish, the benthic fish, and other species of shellfish. And this is the type of data that's been ongoing. So this was not reaching the markets, even though you could go out as an individual and be fishing those areas. In fact, there's been a recovery of some of the stocks there because of the lack of fishing in this region. But I do want to make a point here, and I think it's quite important that, we are going to see an elevation in fish because of this disaster for decades. And if you look on the right here, this is a map showing the location of Chernobyl and that accident, which is now 30 years ago, and the Baltic Sea. And the average concentration in fish there, and I just took some measurements over a 15-year period, is about 7 of these units becquerels per kilogram. The average in Japan, in fact, 4 years later in 2015 was only 2.3 in that data set. So in fact, they're higher in the Baltic today than in most of those Japan samples. But still, if you go out here further in the Pacific and you take the average, it's 0.3. So the point of this is just that you're never going to be back to 0. There already was cesium in the Pacific from our atmospheric nuclear weapons testing, leaving a background level of about 0.3. And so we have to keep this in mind. These are well below limits of 100 or 500 in Europe, but it will be with us for decades until these isotopes decay. In this case, cesium-137, with its 30-year half-life, will take several hundred years before most of it has disappeared because of radioactive decay processes. So I also want to talk about something that we didn't expect when we went out and sampled the ocean. Here's a map of Japan. Again, you can see Fukushima Daiichi as the star here. And we went up and down, not only sampling in the ocean, but also wells, other with colleagues, rivers, and we're going to talk about some groundwater sampling. So what you do in that case is you'd head to the local beaches. You can see these are still being actively used. We would set up our equipment. We would dig holes. We would pump out the tubing as a way to extract groundwater, the liquid that's below the sand. And we took samples of these beaches at many different locations here up and down the coast. I'm going to show you some data from Yotsukura, which is here about 35 kilometers south of Fukushima Daiichi, to give an idea of what we found in that area. So I'm going to show, I think, 3 of these slides that basically have the same axes. Again, cesium-137, we should be familiar by now, becquerels per cubic meter in that unit. I put a couple lines on here, that number near 1 or 2, that's the level before the accident in the ocean, in seawater. And I put a number here that was kind of an average after 2011 in the ocean. And these are plotted versus salinity, because when you're sampling groundwater, you can go from completely fresh waters to salty waters when you take your samples, and that would have an impact on the level of cesium depending upon its source. And so as we sampled different wells and rivers, we got numbers that were quite low, well below this 1,000 threshold for drinking water. So we knew that on land anyway, cesium was not abundant in fresh water. We actually know that from prior studies. It tends to absorb to soils. Yes, there's great concern on land with cesium levels in soils where it attaches to clay, but not in the fresh water that runs through those. So if you go out here in the surf zone, you just walk out, I had a picture of a surfer on that last thing, and go out where they're surfing. And yes, levels are higher, particularly near that beach. And so we wanted to understand why they might be higher in the ocean than what was coming from land. And that's why we went to those different locations and took samples from the wells. We call this groundwater. It's from those beaches, the points I showed you. And again, as we've been doing, every dot here, in this case red, is a sample collected now at different salinities from fresh to ocean. So we'd call this brackish water in the middle. And you can see some quite high numbers. Here's our drinking water limit. We get above that in some of the beaches. Here is the level at the time. This was in 2016. The levels in the harbor ranged from several hundred to just over 1,000. And so we actually found levels. This is now about a meter below your feet on the beach that were higher than in the harbor. Now you also have to wonder, well, is that okay? And how much is getting into the ocean? Some of that is, those are the blue dots, but not as much as is there in the beach itself in those groundwaters. But it certainly was a surprise to us. We never expected to be measuring levels as high as 20-something thousand becquerels per cubic meter in 2016 in the beaches. So this was a surprise to us. We went back several times at several locations to find this. So the question is, where is that cesium coming from? Well, One place are the beach sands themselves. What I showed you in the last plot were just the liquid, the groundwater. So the sands, we would dig holes, we would excavate down to where you found the groundwater. And indeed, at those levels, so this is the top of the beach, this is down a full meter here, and you do see higher levels of cesium associated with the beach sand deeper at this particular location. Now, a different beach, it might be at a different level. So what's really going on, and this is quite important, is that we know there's a source. We know the highest levels are below those beach sands. And the source had to be, in our opinion, we published this data, the absorption back in 2011. Remember I showed you there were millions of becquerels in the ocean at that time, moving south along the beach with those ocean currents and contaminating those sands. And those sands continue to release radioactive forms of cesium even today. I'm going to show you in the next slide how much that is, because that's quite important, not just the level in the beach where it actually is quite fine to be there as a beachgoer, as a surfer, but we want to know, what controls that level in the ocean today, how will it change in time? So we needed to quantify how much was getting into the ocean. And to do that, we go back, we've been there in 2018, we're going to go again in 2021 to see how those levels change over time. So how much, that's just kind of a summary of what we know about the accident itself in 2011. During about the first month until early April, the atmospheric deposition, the fallout, that is both on land, but about 80% of the ocean, released about 15 to 20 petabecquerels of cesium, the isotope we've talked about so far, cesium-137. A petabecquerel is a very large unit, so 1 with 15 zeros. So this is a big number. This is why the levels in the ocean were so high. And they were high because of a direct discharge of cooling waters into the ocean, some of which continues to this day. But again, these numbers are quite high. If you compare it to those ongoing releases, and we have estimates of this from many different methods, including from Japanese scientists looking at the harbor tidal exchange. I'm using that same unit, petabecquerels, but how much is coming out per year, not per the first month. And it's 0.01, something much smaller than today, about 1,000th of times smaller, but still ongoing. So we do need to be concerned. We need to monitor that, and we want to reduce that as much as we can. Something that's harder to reduce are things like river runoff. Most of the cesium, as I mentioned, is retained by soils on land, but during heavy rains and storms, a lot of that does get into the ocean, but still per year, not very much compared to 2011, about the same amount coming out the rivers as from the power plant. And then our new finding is that the releases from the beach sands down here, if you can read the units, also up to about 0.01. So basically the same magnitude as the reactor and the rivers. So if you can completely shut down one source, you'll still have these other sources that are basically impossible to stop or control. So the main point here is that yes, we have ongoing sources. We need to be concerned about these, but we'll get to some future concerns that I actually worry more about than the ongoing releases from rivers, groundwater, or the plant itself. So that's where we're at today, and I think where we will be for decades to come, because it's hard to shut these down to zero. So what are those remaining issues? Well, one of them that I think you may have read about are these thousands of tanks. Every day they have to continue cooling down even the molten cores that remain buried beneath the surface, basically in buildings that are cracked, so groundwater gets in there and cooling water is actively pumped in there. As that water recirculates, more and more gets in because of groundwater flow, somewhere around a couple hundred tons per day. That's being stored, it's being cleaned up to a significant degree. By that I mean removed many isotopes, but there's still radioactivity that remains, which is why they have to put it in tanks here as they decide what to do with that. So right now, 2021, there's over 1.2 million tons of water. This is in over 1,000 tanks. Some were not designed to be there for decades, so they're concerned about what to do about that ever increasing volume. What you'll read a lot in the press and what the Japanese government is talking about is what to do with tritium. That's the most difficult isotope to remove. Tritium is a radioactive form of hydrogen. remember your basic chemistry, H2 is a hydrogen atom. And so it's very difficult to get that form of water, hydrogen, out of water. So it's one of the hardest ones to remove. Now, if it's released slowly, they might not exceed their regulatory limits. But you have to remember, all nuclear power plants are permitted to release tritium and other isotopes. That's because it's considered a low health risk. And the ocean already has a lot of tritium in it because of those nuclear weapons tests. And there's actually naturally occurring tritium. So if you just think of that one isotope, concerns are quite low, and that's why they are considering ocean releases. However, what's in those tanks has been cleaned up, but it's not 100% effective. So even if it's 99.9% effective, if the levels are quite high, you still have a residual non-tritium isotopes that are of concern. And that's what struck us from the beginning. We didn't learn, the public, until 2018 about the levels of things like ruthenium-106, strontium-90, technetium-99, but those are at levels. So what I want to do in the next few slides as I end up is go through what are those levels in the tanks and what should our concern be. So the way I did that is I, again, went onto a public website that the Japanese have, took data from 200 tanks, 200 of the 1,000 they had analyzed, and they put the levels of different isotopes. Here's our friend tritium over here on the left, and 9 other radionuclides that they reported the activity levels in. It's kind of a weird graph because the numbers range quite dramatically between tanks, but by far the remaining tritium has the highest radioactivity levels. This is becquerels per liter. If we look at our unit we've been using so far, that's almost 1 billion becquerels per liter, quite high, but again, less harmful. So that's what they're looking at in those individual tanks. But what worries me more about these other levels, and what we have here in different colors, the yellow line is kind of the average of those 200 tanks, and say the dark blue, half the tanks are within this range. So let's go over here like the strontium-90, which has some tanks, if you look at the total range, that are quite high, up to these levels that are much higher than were ever in the ocean, down to levels that are very low. So we have a highly variable tank farm in terms of different isotopes at different levels. And that is of concern simply because they're not allowed to release some of these higher levels. So how will they manage that? How will they do that in the future? We'll get to that in the next couple of slides. The other thing is an oceanography that worries me actually even more are the differences in the behavior when you put these isotopes in the ocean. We talked about cesium moving with ocean as a soluble radionuclide. Tritium behaves like water, that's the same thing. But if you look at their concentration, their uptake into marine biota like fish, and you look at the light blue color here, jumping to carbon-14, it's more than 10,000 times more likely than tritium to end up in seafood for the same level in seawater. So you put the same level in an aquarium or in seawater, you would accumulate higher levels of cesium. In fact, all of these isotopes would be enriched in marine biota fish at higher levels than the tritium. The other one is the dark blue. That's the affinity for the seafloor, how much of the isotope would end up locally contained by the seafloor sediments. Again, tritium down here at 1, things like cobalt-60 over 100,000 times more likely to be on the seafloor. So it wouldn't follow that model of mixing and dilution. It would start accumulating as they release from each tank and become at higher and higher levels. And finally, so I've talked about the sediment partitioning, the biological health risks. Here we've plotted them. So the smallest health risks are here on the left. Again, tritium, something called the dose coefficient. That's a measure of a certain amount of radioactivity, the human health effects. It's down here on the left. Strontium-90, cesium, iodine are about 1,000 times higher in this same assessment. So your much more dangerous isotopes are here, maybe at lower levels, but still higher affinity for seafloor seafood. So kind of to put that in scale of fish, bioaccumulation, we know that cesium behaves a lot like potassium. It goes in and out of fish and actually our system relatively quickly in weeks. It doesn't stay there. So if you stop the source, levels decrease, as I showed you in the fish that are there today. And if you look at things like tritium, that passes through even quicker. Again, another reason you wouldn't be concerned about tritium in seafood is it behaves like water, goes in and out of fish very quickly, most of it. There are organic forms that stay around longer, but the form that is similar to water goes quickly. Here on the right, strontium 90, it takes years because strontium is taken up in bones, behaves chemically similar to calcium. So each of these isotopes has a different fate in the ocean. And we summarized that in this paper, looking at the allowable release rates. You can see quite a difference. You can release more tritium than things like strontium and cesium. The food limits follow the same trend. And they have different times for their radioactive decay, from a year or two to many millions of years. So that will also have an impact. So kind of in conclusion for this last part of the talk, I certainly think that additional cleanup is needed, and the government says they will do that, but we haven't seen that done yet to a significant degree. I believe we need more independent testing of those levels. I've shown you today just data from TEPCO, the company that's in charge of the cleanup. I think there are more isotopes than just those 9 we need to be concerned about, things like plutonium, things that are even more dangerous. Now, we should fully realize that it's going to take decades to clean this up, so we do need to reconsider storage options. How do you safely store in an earthquake-prone area? But as you store, if you just look at example, say 60 years or 50 years out, many isotopes like tritium itself will decay and disappear in that sense. It has a 12-year half-life. And so it's almost half of it's gone already because of radioactive decay. And then as an oceanographer, I certainly would support testing before, during, and after any sort of releases. And again, not just tritium, but this wider suite of contaminants. And we need to monitor not just seawater, but the seafloor sediments and the marine biota. And I have not heard detailed plans about this. I have heard that they need to make a decision quickly because they're running out of space to store that, but that's more of a political decision than I think a scientifically sound decision. And so I'll just end with this slide. I'll make a plug. It's been my pleasure to be here. I'll be hosting another event on March 4th, streamed out of Woods Hole. You can register for, and we have basically a panel that goes on, time for Tokyo in the evening and the US East Coast 7 o'clock, with an agenda that talks about what happened, the consequences again in the ocean, biological uptake, and a bit about communication of these risks to society. So with that, I'll end here, and thank you very much for your attention. Thank you.